In this video, we're going to be proving some combinatorial identities using a few simple integrals. So the first identity, well, I'm not going to tell you what the answer is. I'm just going to give you the expression, and the goal is to simplify it. So I take a positive integer, n. It's 1 times n choose 0 minus a half n choose 1 plus a third n choose 2 minus a quarter n choose 3, and so on, up to minus 1 to the n over n plus 1 times n choose n. And then the goal is to figure out what this simplifies to. Well, whenever you're trying to prove some combinatorial identity, a good thing to do is to try some values. So let's just try some. Okay, when n is 1, well, what do I get? I get 1 times 1 choose 0 minus a half, 1 choose 1. So that's 1 minus a half, a half. When n is 2, I get 1 minus a half times 2, which is 1, plus a third, which is a third. When n is 3, I get 1 minus a half times 3, plus a third times 3, minus a quarter times 1. Okay, this is a little trickier. So I have these two add up to 2, then I'm subtracting 3 halves, so that's a half, and then I subtract 1 more quarter, so that's 1 quarter. Okay, so we have a half, a third, quarter, so, well, you have to be a little careful just using 3 examples to guess the answer, but a good guess would be that it's 1 over n plus 1. Now, how are we going to prove this? Well, we're just going to use the simple fact that the integral from 0 to 1 of t to the k is 1 over k plus 1. Okay, that's really all we're going to need. Now, that means that this 1 here I can write as the integral of t to the 0. This is the integral of t to the 1, t squared, t cubed, all the way up to t to the n. Okay, so the whole thing is just the integral of n choose 0 minus n choose 1 t plus n choose 2 t squared, and so on. Okay, but now what is this? Well, it's just exactly 1 minus t to the nth power from the binomial theorem. So this is the integral from 0 to 1 of 1 minus t to the nth power. And that's the same thing as the integral of t to the n because of the symmetry. So sure enough, you get 1 over n plus 1. Now a second identity we're going to look at looks very similar, but it's actually quite a bit trickier. So it's n choose 1 minus a half n choose 2 plus a third n choose 3, and so on, up to minus 1 to the n plus 1 over n times n choose n. Okay, so this looks very similar to the previous identity. The only real difference is that rather than starting at n choose 0, we're starting at n choose 1. Okay, so we're going to use the same trick though. So this is the integral from 0 to 1 of n choose 1 minus n choose 2 t plus n choose 3 t squared, and so on. Okay, maybe I'll actually write this power of minus 1 as n minus 1. Okay, so this is almost the binomial expansion of 1 minus t to the n, but not quite, because I've divided out by some powers of t. So what I've done is I've taken 1 minus t to the n, I've removed the constant term, and so I have 1 minus this whole thing, and then I've lowered all the powers by 1. So what I actually have is this. Okay, so this is the thing I'm integrating. Now, that looks bad, but we're going to use the symmetry argument again. So I can just replace t with 1 minus t, and then the numerator becomes 1 minus t to the n, and the denominator of t becomes 1 minus t. Okay, now this I can expand as a geometric series. It's 1 plus t squared all the way up to t to the n minus 1. And when I integrate one term at a time, I get 1 plus a half plus a third, and so on, up to 1 over n. So it's the nth harmonic number. So that gives us the identity n choose 1 minus a half n choose 2 plus a third n choose 3, and so on, equals the nth harmonic number.